Each cattle leg bone shows a clearly tubular shape with dense walls and open marrow centers, making them ideal for controlled mineral extraction. Nine thermal degreasing chambers gently heat the cattle leg bones, melting the remaining animal fat and allowing it to separate cleanly from mineral tissue. "12 optical inspection systems confirm uniform color, shape consistency, and structural integrity across all Angus cattle leg bones. Sensors continuously monitor weight, spacing, and throughput, keeping the cattle leg bone intake line balanced and uninterrupted.
With organic residue removed and mineral structure preserved, the Angus cattle leg bones are now fully prepared.
Each cattle leg bone displays a dense tubular structure with clearly defined ends, allowing consistent heat penetration during later calcination stages. Automated alignment rollers rotate the cattle leg bones slowly, checking straightness and surface integrity before thermal exposure. Infrared scanners analyze moisture levels inside the cattle leg bones, confirming they meet strict dryness thresholds required for controlled mineral conversion.
The cattle leg bones pass through preheating tunnels, where gradual temperature rise prevents cranking and preserves internal calcium structure.
Any Hereford cattle leg bones showing structural fractures or abnormal density are automatically diverted from the line to maintain mineral consistency. 23 accepted cattle leg bones continue forward in evenly spaced intervals, preventing overlap and ensuring uniform thermal loading. Controlled airflow removes residual internal moisture from the cattle leg bones, reducing vapor expansion during calcination. 29 The Charolais cattle leg bones enter buffer zones, where temperature and spacing are synchronized before furnace entry. With geometry stabilized and moisture eliminated, the cattle leg bones are now fully prepared for high-temperature conversion into bone ash.
The surface of each cattle leg bone appears dry, pale, and matte, signaling readiness for extreme heat transformation.
Continuous rotation ensures each cattle leg bone receives uniform heat distribution across its full cylindrical length.
The fully calcined cattle leg bones emerge as lightweight, chalky bone ash with a dry, porous texture.
43 cooling tunnels expose the bone ash to filtered ambient air, stabilizing mineral composition and preventing moisture absorption. As temperatures normalize, the bone ash appears uniformly white, indicating complete organic removal. At this stage, the cattle leg bones have been fully transformed into pure bone ash, ready for fine grinding and mineral refinement. The crushed bone ash moves through multi-stage milling systems, gradually reducing particle size while preserving calcium phosphate crystal integrity. 50 high-speed ball mills grind the bone ash into an ultra-fine powder, producing a soft, uniform mineral texture suitable for oral care applications. 51 cyclone separators classify the powder by weight and fineness, returning oversized particles for regrinding until specifications are met.
The refined bone ash powder enters purification tanks, where controlled chemical treatment isolates calcium phosphate.
54 filtration systems capture the purified calcium phosphate, while liquid waste streams are safely diverted for neutralization.
The filtered calcium phosphate appears as a bright white, fine-grind mineral with consistent density and smooth tactile properties.
Only calcium phosphate meeting strict toothpaste grade standards advances further along the production line. The calcium phosphate remains free-flowing and uniform, ensuring predictable behavior during toothpaste formulation.
At this stage, purified calcium phosphate is fully prepared as a key functional ingredient for toothpaste base production.
Stored calcium phosphate is released from stainless steel silos in controlled batches, entering the quality control line.
The analysis confirms the uniform abrasiveness. It's perfectly suitable for daily oral care use.
Excellent news. Let's finalize the report.
68 moisture sensors confirm the calcium phosphate remains dry and free-flowing, preventing clumping during toothpaste formulation.
Data from all tests is compiled into digital quality reports, linking performance metrics to specific calcium phosphate batches.
Any calcium phosphate failing specification is automatically isolated and rerouted for reprocessing or disposal. The calcium phosphate remains stable, bright white, and uniform throughout controlled movement across the factory.
78. Inventory systems update mineral availability in real time, ensuring uninterrupted toothpaste production.
With quality approval complete, calcium phosphate is now officially cleared as a functional ingredient for toothpaste base formulation.
80 approved calcium phosphate is metered precisely into large stainless steel mixing vessels, forming the primary abrasive foundation of the toothpaste base formulation.
81. Deionized water is added gradually, allowing the calcium phosphate to disperse evenly and begin forming a smooth mineral suspension. 82. Humectants such as glycerin and sorbitol are introduced, controlling moisture retention and preventing the toothpaste base from drying out. 84. Thickening agents are dosed carefully, increasing viscosity and transforming the mixture from liquid slurry into a cohesive paste structure. 85. Temperature control jackets maintain stable mixing conditions, preventing premature thickening or separation during base formation.
86. Continuous sensors monitor viscosity, density, and flow behavior of the toothpaste base in real time.
87 additional stabilizers are blended in small quantities, improving long-term consistency and shelf stability of the toothpaste base.
89. Inline homogenizers refine the toothpaste base further, breaking down microagglomerates for a consistent mouthfeel. Process control systems adjust mixing speed automatically, responding to viscosity changes during formulation. 93 approved toothpaste base is directed toward final ingredient integration zones.
95. At this stage, the toothpaste base is fully formed and ready for final mixing with functional and sensory ingredients. The prepared toothpaste base enters high-capacity final mixing tanks, where enclosed systems prevent air exposure during advanced processing.
The toothpaste mixture becomes smoother and more cohesive as internal particle distribution reaches equilibrium.
6. Vacuum deaeration units remove trapped air bubbles, preventing foaming and ensuring consistent density.
The toothpaste achieves a glossy, uniform appearance, indicating full ingredient integration.
At this point, the toothpaste is fully finalized and ready for tube filling and sealing operations.
The toothpaste settles smoothly inside the tubes, free from trapped air due to prior vacuum deaeration.
Heat-sealing jaws apply controlled temperature and pressure, permanently closing each toothpaste tube.
Stage 31, fully prepared for final packaging and display.
The toothpaste products now appear fully packaged, labeled, and traceable throughout the distribution chain. The toothpaste products now appear full-finished, branded, and ready for global markets. 40 Vision inspection systems confirm label accuracy, readability, and correct product identification on every sealed box.